Muito bem, bom dia, boa tarde, boa noite, né? Depende da hora que vocês vão estar assistindo esse vídeo. Então, o objetivo aqui, turma, em cálculo 4, séries de Fourier, né? A ideia é mostrar algumas aplicações das séries de Fourier, né? E que de certa forma também discute um pouquinho de transformadas, né? Mas muito mais para vocês entenderem aí a real necessidade, né? De estudar séries de Fourier em engenharia elétrica. Vocês vão perceber que no vídeo dá-se uma ênfase maior, né, a forma complexa, tá certo? Então é isso. Detalhe importante, eu vou estar colocando um vídeo de semestres anteriores, então um recorte cola aí, tá certo? Então o objetivo principal dessa aula é apresentar para vocês alguns vídeos que eu descobri aqui no canal do YouTube, né, que tratam da transformada de Fourier e que, de certa forma, facilita esse entendimento. E aí, na próxima aula de amanhã, a gente possa resolver o exercício, né? Vocês viram que não chegamos no final, né? A gente retoma aquele exercício e dá sequência, certo? Então, esse é o objetivo principal. Então, vamos lá. Deixa eu compartilhar com vocês aqui a tela. Beleza, eu coloquei aqui no chat para vocês os links, né, desses vídeos, né? Depois vocês também podem tá pegando pelo chat, tá? Apesar que eu não sei, né? Que não é ao vivo, né? É uma aula A5, né? Bom, mas de qualquer forma eu deixo para vocês lá no Class os links desses vídeos, tá? Então vamos começar por esse daqui, que ele vai falar da transformada do mundo da ciência, né? Vai falar sobre a transformada de Fourier. Então vamos lá.
Olá pessoal, sejam bem-vindos a mais um vídeo do canal O Mundo da Ciência. Hoje vamos falar da transformada de Fourier, uma transformada integral utilizada tanto na física como na análise de sinais, sendo responsável, por exemplo, por converter arquivos de áudio para o formato de MP3, bem como processar imagens. A transformada leva o nome do matemático francês Jean-Baptiste Fourier, que resolveu a equação do calor utilizando uma série trigonométrica, série a qual leva seu nome. A transformada de Fourier é uma das ferramentas matemáticas mais importantes do mundo moderno, e apesar de ter surgido no século XVIII, foi com o surgimento das mídias digitais que ela se popularizou. Imagine uma função periódica. Uma função periódica é aquela que, após um período t, obtemos o mesmo valor. Podemos representar funções periódicas como somas de senos e cossenos. Essa é a chamada série de Fourier. Podemos utilizar as séries de Fourier para resolver a equação do calor e a equação da onda, dada uma condição de contorno. Então, aqui está a primeira aplicação: resolução de equações diferenciais parciais de segunda ordem com uma condição de contorno. Um sinal pode ter várias frequências, vários componentes, como uma música que possui várias notas, ou seja, várias frequências e muitas delas tocadas em simultâneo e possuindo amplitudes diferentes. Então, podemos considerar um sinal como uma soma de senos e cossenos, exatamente como numa série de Fourier. Uma música, por exemplo, é composta por várias componentes, cada uma com uma frequência e amplitude diferente. um sinal dividido em suas várias componentes forma um espaço vetorial, o espaço L2, das funções de quadrado integráveis, que é um tipo de espaço de Hilbert, o mesmo espaço vetorial utilizado para descrever os fenômenos quânticos. Podemos analisar um sinal e ver quais componentes compõem esse sinal. A isso chamamos de análise de Fourier. Peguemos uma função cosseno ou seno, por exemplo. Se o sinal f de t conter essa componente, o produto interno da componente pelo sinal dará 1. Caso contrário, dará 0. Isso porque funções cossenos, que são múltiplos de uma frequência fundamental, são ortogonais entre si. Por exemplo, cosseno de 2π mt é ortogonal a cosseno de 2π nt, caso n seja diferente de n.
Aqui, turma, então tem aquela particularidade. A gente mostrou, já resolvemos essa integral na aula anterior, né? E que, de fato, deu 0 se o m é diferente de n, né? E deu 1 se o m é igual a n. Nesse caso aqui, ele está dizendo que é 1 porque está indo de 0 a t, tá? No nosso caso lá, deu p, né? Já vai explicar por que dá 1. Mas, de modo geral, né? A gente chama isso aqui, então, de funções ortogonais. E por isso que dá 0, tá? Só uma particularidade.
Ou seja, o produto interno dá 0. Mas se n é igual a n, então esses termos são paralelos e, portanto, o produto interno dá 1. Então, se o sinal possui uma componente de frequência Fn, o produto interno retorna 1.
Ele está dizendo que é 1 aqui, turma, muito fácil também observar, né? É assim, não é o que dá 1 aqui é o cosseno vezes cosseno, né? Então, quando a gente resolve no intervalo de 0 até t, né? Então, a gente vai ter que isso aqui é 1 dt, que a variável aqui é t, né? Então, esse 1 dt, então a gente vai ter t no intervalo de 0 a t. T no intervalo de 0 a t é t. Tá certo? Então, esse 1 que ele apresenta aqui é, na verdade, o produto dos cossenos em relação a esse produto. Tá?
Compreendem a importância disso? É como pegar uma música e perguntar se nessa música existe uma nota dó da terceira oitava ou a nota lá da quinta oitava. É analisar um sinal em cada uma de suas frequências. Podemos representar uma soma de cosseno e seno por um número complexo, utilizando a fórmula de Euler, e podemos converter a frequência em frequência angular. A série de Fourier é muito boa para representar funções periódicas, mas se queremos representar uma função genérica, um sinal genérico, que pode ser não periódico, então devemos utilizar a transformada de Fourier. A transformada de Fourier é uma transformada de domínio, uma transformação linear, que transforma um sinal como função do tempo em um sinal como função da frequência. Até agora, analisamos um sinal como função do tempo, um f de t. Porém, em muitos casos, é interessante estudar um sinal como função da frequência, um f de ômega. A transformada de Fourier faz esse trabalho. O processo contrário é a transformada inversa de Fourier, que converte um sinal do domínio da frequência para o domínio do tempo. Tendo agora a ferramenta matemática da transformada de Fourier, podemos analisar as frequências que compõem um sinal e suas respectivas intensidades. Podemos analisar o espectro de um sinal, e isso é extremamente útil, como vou mostrar. Por exemplo, o áudio digital, o famoso MP3, é fruto da transformada de Fourier. Quando um áudio é gravado em uma gravadora, muitas faixas de frequência são ruídos ou também faixas de direitos autorais. Podemos localizar essas frequências inúteis, que são somente ruídos, e eliminá-las, deixando o arquivo de áudio bem mais leve. Podemos fazer o mesmo processo com sinais de TV e rádio. Também podemos usar a transformada de Fourier para estudar regimes transientes em circuitos elétricos RLC, de corrente alternada. E podemos utilizar a transformada de Fourier para resolver a equação de Schrödinger na mecânica quântica, bem como representar estados quânticos como função da posição ou do momento. Até agora, vimos a transformada de Fourier para tempo contínuo. Porém, para ser usada por métodos computacionais, é necessário que discretizemos o tempo, dando origem à transformada de Fourier de tempo discreto. Dessa forma, podemos implementar a análise de Fourier de sinais digitais, como áudio e imagens.
Então, turma, quando vai para a proposta computacional, óbvio que o computador não consegue calcular de forma contínua. Né? Então, o que o computador faz é transformar o contínuo em discreto. Tá? Então, só essa diferença.
Dando algoritmos computacionais, como a transformada rápida de Fourier.
Aqui está uma linguagem Python, né? Computacional. Estou aprendendo, isso é muito interessante.
Para o processamento de imagens, utilizamos a transformada discreta de Fourier bidimensional, visto que uma imagem é bidimensional. Fazendo a transformada de Fourier, podemos determinar as frequências que compõem uma imagem e determinar filtros. A ideia da utilização de filtros vem do teorema da convolução, onde se adiciona um sinal ao outro. Adicionando o filtro passa-baixa, realçamos os pixels de baixa frequência, enquanto que adicionando o filtro passa-alta, realçamos os pixels de alta frequência. Desse modo, podemos estudar melhor a imagem e otimizá-la. Utilizando o filtro passa-baixa, destruímos os detalhes da imagem, a imagem menos nítida, porém removemos os ruídos, enquanto que o filtro passa-alta é utilizado quando queremos enfatizar os detalhes da imagem, como, por exemplo, em uma impressão digital. Um uso importante da transformada de Fourier em processamento de imagens é justamente na análise de impressões digitais. Em resumo, as séries de Fourier são séries trigonométricas que representam funções periódicas, enquanto as transformadas de Fourier podem ser usadas para funções não periódicas. Um sinal pode ser representado como somas de senos e cossenos, e, portanto, uma série de Fourier. A transformada de Fourier converte um sinal do domínio do tempo para o domínio da frequência, enquanto que a transformada inversa de Fourier converte o sinal do domínio da frequência para o domínio do tempo. Para ser utilizado em computadores, existe a transformada discreta de Fourier, importante na análise e processamento de imagem. E, por fim, vimos que a transformada de Fourier é importantíssima na análise e processamento de sinais, como áudio, imagens, sinais de TV e rádio, podendo desmembrar um sinal em suas várias frequências componentes e otimizá-los, como, por exemplo, eliminando ruídos.
Tá aí. Acho que essa foi a ideia principal. Uma coisa, vocês viram então que é um vídeo muito mais voltado para a ciência da computação, né? Muito mais aplicado para a ciência da computação, né? Eu queria apenas mostrar aqui um item que eu achei importante, que é, deixa eu ver se eu acho ele fácil aqui, que foi a representação. Peraí. Aqui, isso. Então aqui, deixa eu pegar aqui uma, uma, uma lousa aqui para a gente enxergar isso. Deixa eu mostrar essa lousa para vocês, que é a minha lousa aqui, que acaba sendo muito mais interessante, né? É uma interpretação que a gente faz, que é essa daqui, ó. Cadê? Não abriu? Deixa eu abrir de novo, porque acho que... deu problema. Vamos ver se agora vai. Pronto, agora foi. Então, é isso aqui, turma. Isso aqui é o que me interessa. Vocês estão vendo aqui, quando eu observo, né, essas curvas trigonométricas, né, ou essas funções trigonométricas por aqui, eu acabo enxergando que esse eixo aqui é o meu domínio, é o tempo. Então, quando eu observo o tempo, quando eu observo estas curvas, o que eu enxergo? Todas misturadas, vendo todas de frente, né? Altos e baixos, né? Então eu consigo enxergar num primeiro instante, né? Que de fato elas estão todas ali misturadas, né? Agora, quando eu troco o eixo por frequência, porque aqui a gente teria ó, a frequência em relação ao tempo, na verdade aqui seria, né? Aqui eu tenho a amplitude do gráfico, né? E aqui, então, esse eixo seria o tempo, e eu estou analisando o tempo em relação à sua amplitude. Agora, aqui eu troquei. Olha só, eu estou enxergando aqueles gráficos por aqui. Quando eu enxergo por aqui, eu estou vendo a frequência. Ou seja, essa é uma outra visão. Aqui eu não estou analisando o tempo, e sim a amplitude. E, na verdade, percebam que Fourier não vai trabalhar com a amplitude toda. Ele vai trabalhar só com a ideia da amplitude positiva, de zero, né, até o extremo da minha amplitude, né? Então, ele não trabalha com aquela amplitude toda. Como vocês viram em diversos momentos, na aula passada, até a gente nem calculava de menos P até zero, já calculava de zero até P, em função disso, tá certo? Então, essa é a particularidade desse vídeo que acaba sendo interessante. Então, aqui, de fato, a todo instante, e aí o que vai fazer? Se numa transformada eu estou trabalhando com o tempo, também tem, então, se eu parto do tempo, que é essa ideia aqui, ó, então, se eu parto do tempo, né, eu tenho a possibilidade de calcular a inversa, e se eu tenho, por exemplo, então, se eu parto da variável tempo, eu chego na frequência. Eu chego, então, num resultado que é exatamente a minha função que depende da frequência, que é essa daqui, ó. Agora, quando eu faço a inversa, eu volto para essa aqui. Ou seja, a gente vai trabalhar a todo instante muito parecido lá com Laplace, né? Então é isso. Esse seria o primeiro vídeo. Vamos para um segundo vídeo. Esse vídeo aqui, deixa eu ver se ele é interessante para vocês nesse instante. Deixa eu só lembrar aqui, mas acho que, vamos lá. Ele vai falar da discreta. A discreta, como vocês viram, é muito mais computacional. Vamos ver se a gente deixa ele para o final. Vamos mostrar esse aqui, que ele é mais interessante. Propaganda, né? Estou interessado em propaganda.
We have an x-axis and a y-axis. Let us also create an axis that represents the angle theta. The green line rotates by the angle theta. For each value of theta, the x-coordinate represents the cosine of theta, and the y-coordinate represents the sine of theta. The angle theta can range anywhere between negative infinity and positive infinity. This two-dimensional pattern is what we refer to as a sine wave. We can change the sine wave's amplitude, phase, and frequency. Suppose we have two sine waves that are identical except for the fact that they have different amplitudes. If we add these two sine waves together, the result can be represented graphically as shown. Now, suppose that the two sine waves also have different phases. The sum of waveforms can be represented graphically like this. So long as the two sine waves have the same frequency, their sum will always be another sine wave of the exact same frequency, but with a different amplitude and phase.
Pessoal, aqui também é importante vocês observarem por que ela diz que a frequência é a mesma. Por causa disso aqui, né? Olha lá. Aqui, na verdade, a gente tem uma translação, né? Tá certo? Em relação ao eixo X, que no caso é o ângulo, né? Então, perceba que aqui o período é o mesmo, né? Então, se o período é o mesmo, por isso que a gente não tem essa alteração, tá?
Now, suppose that the sine waves also have a different frequency.
Ó, percebam que agora mudou. Então, o período dessa senoide é diferente do período dessa senoide. Enquanto essa está tendo um período de 360, essa que está aqui está tendo um período de 120 graus. Então, isso aqui faz uma volta a cada 120, enquanto que esse daqui faz uma volta a cada 360. certo? Então, mudou o período de ambas, e aí por isso que o comportamento está mudando. Ó.
If we add together sine waves of different frequencies, then the resultant waveform is no longer a sine wave.
Então, o fato de terem períodos diferentes está resultando em frequências, né, diferentes.
We can add together 3 sine waves. We can add together 4 sine waves. We can add together 5 sine waves. In fact, we can add together an infinite number of sine waves. Here, by adding together an infinite number of sine waves, we have produced a pattern that looks like this. Now, let's add together a different set of sine waves. By adding an infinite number of sine waves, we have produced this other pattern that looks like this. As it turns out, every possible waveform and function in existence can be generated by adding together different sets of sine waves. In the two examples, happened to be repeating waveforms. In these cases, only certain frequencies of sine waves were needed. And each of these sine waves had a measurable amplitude. Non-repeating waveforms can also be generated adding sine waves together. But in these cases, sine waves of every possible frequency may be needed. And each of these sine waves have an amplitude that is infinitely small. When an infinite number of sine waves with infinitely small amplitudes are added together, the result can be a waveform that we can see and measure. This is the same way in which, if we add together an infinite number of infinitely thin sheets of paper, although each sheet of paper by itself has zero volume, their combination can be an object with an actual volume that we can see and measure. Some sheets of paper can be larger than others. Although the volume of each sheet of paper by itself is zero, when we have an infinite number of sheets of paper added together, we will be able to measure the object's density. And the density in some parts of the object will be higher than the density in other parts of the object. Similarly, when we add together an infinite number of sine waves of infinitely small amplitudes, we will be able to measure the density of frequencies. And this density of frequencies will be higher around some frequencies than others.
Pessoal, aqui é legal, por exemplo, enxergar que cada domínio da frequência representa a amplitude de cada uma dessas funções trigonométricas, sejam senoidais, cossenoidais, né? É essa a ideia, tá?
This is what we refer to as the frequency spectrum of a waveform. All signals and waveforms have a frequency spectrum. When signals and waveforms interact with physical objects, their frequency spectrum is altered. By understanding how the frequency spectrums are altered, we can understand how the signals and waveforms are altered. The signals and waveforms that we see in real life have a beginning and an end. However, each of these signals and waveforms can be thought of as the combination of an infinite number of sine waves, and each sine wave has no beginning or ending. It is just that all these sine waves exactly cancel each other out at all times, except during the time that the signal is present. Therefore, all signals that we see in real life can be thought of as the combination of an infinite number of sine waves that have always been present since the beginning of time, and which will continue to exist through all eternity.
Pessoal, quando ela usa o termo combinação de funções, a gente está falando lá daquela história da álgebra linear, né, do espaço vetorial. O espaço vetorial, na verdade, ele é uma combinação de vetores. Os vetores aqui são pensados como funções, tá certo? Que nada mais é do que essa ideia mesmo, um vetor que parte até um certo ponto, tá? Em 3D. O único detalhe é que o vetor ele é uma combinação de outros vetores, né? Então, ele pode ser, então, um vetor do ponto de vista de função, ele pode ser uma combinação de outras funções.
More information about mathematics is available in the other videos on this channel, and please subscribe for notifications when new videos are ready.
Um vídeo interessante, né? Foi só para mostrar mais essa ideia aí da animação, né? Vocês veem que no Brasil ainda não temos essa condição, né? Os vídeos lá fora são muito mais interessantes, né? Nós aqui muitas vezes ficamos só no cálculo, né? Queríamos, vamos aproveitar já que ele falou lá das animações, vamos pegar isso daqui. A gente tem aqui séries de Fourier. Envolvendo a explanação de...
What up? Today we're going to talk about waves. This is a circle. You probably knew that. If we were to turn this circle on, I want you to go up and down and trace that motion out, you get what's called a sine wave, which you know to be important in things like pendulum motion, particle physics, things of that nature. Sine waves are important. But for my money, the coolest thing about it is you can add them together to do other things, which sounds simple until you realize this is how the 2018 Nobel Prize in Physics was won. My buddy Brady Heron has a really good video about that over on 60 Symbols. So there's some fancy math I learned at the university called the Fourier series. These are my old notebooks. And check this out. The teacher challenged us to create this graph by doing nothing but adding together curves. And I found where I did it. It's right here. And it took me, it looks like 4 or 5 pages. Yeah, it took a lot of pages. And I ended up with this. I was able to make the graph by adding together a bunch of waves. And to demonstrate that, I created this. I had to get a tripod. Here's my flipbook. So it starts with one sine wave, and then we add another one. And you can see the more waves you add together, the closer the function gets to what you're supposed to make. Because you can see like that and that look very similar. That's 50 waves added together. So it's cool, and it's one thing to know how to do the Fourier series by hand. It's quite another to understand how it works. And I didn't really have that moment of it clicking in my brain until I saw this awful.
Isso, então, ó, uma coisa, por isso que é importante esse tipo de vídeo, né? Algo importante é vocês saberem calcular. Agora, eu acho que muito mais é, muitas vezes, enxergar aplicações disso, né? É nesse sentido que ele está dizendo. Então, o professor propôs para ele que ele resolvesse lá, encontrasse a função da transformada de Fourier que se aproxima-se daquela função inicial. E ele resolveu, né? Mas não ficou satisfeito.
awesome blog by a guy named Doha from Turkey. He's a student at Georgia Tech. I want to show you this. This made it click in my mind, unlike anything. This transcends language. So let's go check out Doha and let him teach you how a Fourier series works. I'm in Georgia Tech. This is Doha. Hello. You have visualized via animation a Fourier series in the most beautiful way I've ever seen in my life. Sine waves are probably the simplest kind of wave, right? The second most simple kind of wave is a square wave. But the difference is you have sharp edges in a square wave. The first thing that Doha did to impress me is he used curvy waves to make sharp-edged square waves. We have to add up different oscillations or simple harmonic motion here.
Harmonic, yes.
Yeah, and so the first harmonic, n equals 1, gives you this,
Yes.
which looks nothing like it.
Nothing interesting, just boring sine wave. And I add one more. It's actually like a, I'm adding one harmonic and other one third of that harmonic.
So you're adding a basic, what are we going to call these, wipers?
Yeah, let's call them wipers.
Okay, so we're going to add a wiper on a wiper. And by doing that, and we graph the function.
And then follow the tip of these wipers.
Yeah.
And draw that this next time.
It's awesome, man.
Yes.
Like this is really, really beautiful and really, really simple.
So I can add more wipers.
Então, turma, aqui, ó, ele está tentando buscar essa função aqui, ó. Né? Está buscando uma transformada de Fourier que se aproxime-se desta função aqui, ó. Né? Então, a transformada que ele vai encontrar, no final das contas, vai gerar isso aqui. E ainda vai ter essa distância. Opa! Ainda vai ter essa distância final aqui. Vamos deixar o vídeo seguir, né? Mas a ideia aqui é vocês enxergarem que ele colocou, olha, ele tinha uma... Aqui já tem 3 funções trigonométricas, todas com períodos diferentes, certo? Essa é a ideia que vocês viram ali no vídeo anterior. E aí segue. Vamos lá.
It is more harmonics. And I add 15 harmonics, something very cool.
Oh, wow, it looks like a whip.
Yes.
So you're saying, so basically, here's the upshot. A Fourier series, you can create any function as a function or an addition of multiple simple harmonic motion components, right?
Yes.
All Doha is doing is he's taking these sine waves that we explained earlier, and he's stacking one on another sine wave. He's stacking the circles to add together these waves to create a Fourier series. These visualization techniques that Doha developed work on any version of any function. For example, on a sawtooth wave, you can see in n equals 8 how the Fourier series starts to play out. It looks really cool. How did you do this? Like, what program did you use to visualize this?
I use Mathematica.
Mathematica?
I had just started as
propaganda, hein?
working on the International
Estudar, né,
Space
turma? Vamos lá.
Station.
That's my place.
Really?
Yes.
So, if I give you any function, you have to flip it into video format somehow. How did you do that?
I told it in like if I created a table of the different times of this animation.
Só para a gente tentar explicar aqui, turma, aquela história do n, quando ele diz n igual a 15, vocês se lembram, então, né, que a função transformada de Fourier, né, ela começa com uma certa constante desse jeito, e aí ela tem um somatório de n igual a... Ela começa no 1, vai até infinito, né? E aí aqui você tem o coeficiente, né? Lá a gente chamou de AN, né? Isso, AN cosseno, né? De N pi x sobre P, né? Mais BN seno de N pi x sobre P. Aqui já dá para vocês terem uma noção, então, dessa história. 15 é que ele pegou, então, o somatório de seno e cosseno. Eu tenho um somatório, eu tenho 15 senos, né? E 15 cossenos. Então, pode ser que no meio do caminho o cosseno precisou anular, o seno precisou anular, ou às vezes não, né? Então, é essa a lógica. Quer dizer, quanto mais quanto mais iterações ele tiver, mais próximo ele conseguiu chegar aí do resultado esperado, né? Então é essa a ideia. Vamos seguir.
And then I just export those tables into GIF.
Okay, here's an interesting question. Are people, it's actually GIF. I don't know if you know that. So if I were to give you a function, if I were to give you a super, super complicated function, like a really weird curve, you could make a graphic like this?
Well, I can.
So I can challenge you.
Yeah.
Let me explain what's happening here. Amongst academics, there's this thing that I just now made up called math swagger. And basically, it's when a person's good at math, they like think they can do anything with it. It's not like a prideful thing. I mean, Doha's a very humble person, but you could tell he's very confident in what his abilities with math were. So I can challenge you.
Yeah.
Which is why I'm challenging him to draw this with the Fourier series. It is that smarter everyday thing that you see all over the internet. I totally geeking out right now. I love this. It's a hard to draw using math. It's got like curves, right? It's got little sharp points and switchbacks. It's self-serving for me. So this is an appropriate challenge for somebody that's demonstrating math swagger. The problem is he actually can do it. He can model this using nothing but circles in the Fourier series, which is completely impressive. Check this out. The first thing that he has to do in order to draw this image is to extract the x and y positions that he would need to make functions for in order to make this thing work. He then needs to create a Fourier series for each one of those functions so that he can add them together. And as you can see, these first few were not winners. I mean, like, no stretch of the imagination your brain think this looks like the side profile of a human head. Everything's a bit derpy. But as he starts to refine it and he adds more and more waves to the functions, things start to hone in and it starts to look really good. At about 40 circles in this whole function, things start to look really good, and your brain would totally think that you're looking at a drawn image instead of a mathematically drawn function. If you look closer at just one of these arms, you would think that it's chaos, but it's not. It's complete order backed up by a mathematical function. In fact, this is why I love math. It's the language that describes the entire physical world. We can approximate.
Pessoal, deixa eu dar uma parada aqui, peraí. Para aí que eu quero parar.
Of the Fourier series. Simple thing.
Dá para ter uma ideia aqui, inicialmente, que foi a primeira impressão que eu tive, por exemplo, uma impressora 3D, né? A impressora 3D, então ela trabalha com as transformadas de Fourier, se a gente pensar do ponto de vista, né, do caminho que ela faz, né?
Things you understand, like oscillators, sine waves, circles, and you could add them together to do something much more complex. And if you think about it, that's all of things, and you build upon them, and you can make a complex system that can do incredible things. A simple thing can lead to something incredibly powerful. Speaking of the power of simple things, I want to say thanks to the sponsor, KiwiCo. I reached out to KiwiCo and asked if the sponsor Smarter Every Day a long time ago, because this can change the world. They send a box to your house for a kid to open and build a project with their hands. They're not on a phone, they're not like on a tablet, they're building something with their hands, and that's going to change how they look at things. So you might like to work on the kit with your child, or it might be important to have a hands-off approach and let them build something on their own and see it through to completion. The kit comes to your house, there's really good instructions in there, the kid gets to work on a project themselves. At the end of the project, they have something they built with their own hands. Ultimately, I just want you to do this for your children or a child you love, and I want more of this in the world. Go to kiwico.com/smarter and select whatever makes most sense for the kid in your life. Get the first.
Vocês viram que no fundo, né, ele acabou né, mostrando aí uma propaganda de um material para experimentos, né? E que, de fato, eu já conheço o Eureka, aqui no Brasil ainda não tem muito, e é algo interessantíssimo, mas ainda é muito caro para nós, até por conta do dólar, né? Mas, por exemplo, em escolas, aqui no IFC, a gente acabou de comprar uns kits de robótica aí, exatamente para tentar trabalhar esse tipo de ação aí, né? Quer dizer, muito mais prático. Assim como vocês, né, que estavam num projeto aí de fazer acho que era são coisas assim que são muito mais interessantes, né? Bom, então esse vídeo aqui, bem bacana, tá? Quero ver se eu consigo chegar àquele desafio ali dele, ali, de pegar, por exemplo, uma imagem qualquer, usando a transformada de Fourier, e conseguir resolver. Bom, vamos para mais uma que também trabalha com a animação. A mesma ideia, tá?
Here we look at the math behind an animation like this one, what's known as a complex.
Propaganda.
Em 2014, eu lancei um documento que denunciava todo o descalabro econômico da equipe da então presidente Dilma Rousseff.
Precisa aprender a baixar vídeo, né, Tom? Que aí... propaganda. Olha lá. É uma série de Fourier complexa. Deixa eu voltar um pouquinho, isso aqui é muito bacana. Nossa. Ele está dizendo que cada vetor está trabalhando do ponto de vista vetorial. Volta aqui, meu filho. Isso.
Here we look at the math behind an animation like this one, what's known as a complex Fourier series. Each little vector is rotating at some constant.
Ixi, não está em português. Peraí, vou tentar colocar em português aqui. Ainda bem que agora tem essa possibilidade de você automaticamente, né? Antigamente era um trabalho danado isso, né? Agora está muito fácil, né? Inclusive o pessoal das lives, aí eu estava esses dias perguntando como é que sai a legenda automática? É automático, né? Eu pensava que era alguém que foi lá e traduziu, que nada. Ué, não foi? Não coloquei português? Vasco, que Vasco. Portuga. Aí.
We can make it drop pretty much anything that we want. And here you'll see how. Before diving into it all, I want you to take a moment to just linger on how striking this is. This particular animation has 300 rotating arrows in total. Go full screen for this if you can. The intricacy is worth it. Think about it.
Quando ele diz 300 setas de vetores, turma, cada vetor vai trabalhar com um certo N, né? Que vai trabalhar com a somatória do cosseno e o seno, mais a constante. Por exemplo, enxergar, né? Então, ali, se são 300, então, haja somatório, né?
The action of each individual arrow is perhaps the simplest thing you could imagine. Rotation at a steady rate. And yet the collection of all added together is anything but simple. And the mind-boggling complexity is put into an even sharper focus the farther we zoom in, revealing the contributions of the littlest, quickest, and downright frenetic arrows. When you consider the chaotic frenzy that you're looking at, and the clockwork rigidity underlying all the motions, it's bizarre how the swarm acts with a kind of coordination to trace out some very specific shape. And unlike much of the emergent complexity you find elsewhere in nature, this is something that we have the math to describe and to control completely. Just by tuning the starting conditions, nothing more, we can make the swarm conspire in all of the right ways to draw anything that you want, provided that you have enough little arrows. Crazier is that the ultimate formula for all of this is incredibly short. Now often, Fourier series are described in terms of something that looks a little different. Functions of real numbers being broken down as a sum of sine functions. That turns out to be a special case of this more general rotating vector phenomenon that we'll build up to, but it's where Fourier himself started, and there's good reason for us to start the story there as well. Technically, this is the Fourier series in a way that doesn't depend on you coming from those chapters, have at least a high-level idea for the problem from physics, which originally motivated this piece of math. It gives some indication for just how unexpectedly far-reaching Fourier series are. We have a certain equation which tells us how the temperature distribution on a rod would evolve over time. And incidentally, it also describes other phenomena unrelated to time. And while it's hard to directly use this equation to figure out what will happen to an arbitrary distribution, There's a simple solution if the initial function just happens to look like a cosine with the
Essa é a equação do calor, como eu mostrou agora.
frequency tubes so that it's flat at each endpoint. Specifically, as you graph what happens over time, these waves simply get scaled down exponentially, with higher frequency waves having a faster exponential decay. The heat equation happens to be what's known in the business as a linear equation, meaning if you know two solutions and you add them up, that sum is a new solution. You can even scale them each by some constant, which gives you some dimes to turn to construct a custom function solving the equation. This is a fairly straightforward logic that you can verify for yourself, but it's incredibly important. It means that we can take our infinite family of solutions, these exponentially decaying cosine waves, scale a few of them by some custom constants of our choosing, and combine them to get a solution for a new, tailor-made initial condition, which is some combination of cosine waves. One important thing I'd like you to notice is that when you combine these waves, because the higher frequency ones decay faster, the sum that you construct will tend to smooth out over time, as all the high frequency terms quickly go to zero, leaving only the low frequency terms dominating. So in a funny way, all of the complexity in the evolution of this heat distribution, which the heat equation implies, is captured by this difference in the decay rates for the different pure frequency components. It's at this point that Fourier gains immortality. I think most normal people at this stage would say, well, I can solve the heat equation when the initial distribution just happens to look like a wave, or a sum of waves. But what a shame, most real-world distributions don't at all look like that. I mean, for example, let's say you brought together two rods, which are each at some uniform temperature, and you wanted to know what happens immediately after they come into contact. To make the number simple, let's say the temperature of the left rod is 1 degree, and the right rod is negative 1 degree. L of the combined two rods is 1. What this means is our initial temperature distribution is a step function, which is so obviously different from a sine wave, or the sum of sine waves, don't you think? I mean, it's almost entirely flat, not wavy, and for God's sake, it's even discontinuous. And yet, Fourier thought to ask a question which seems absurd. How do you express this as a sum of sine waves? Even more boldly, how do you express any initial distribution as a sum of sine waves? And it's more constrained than just that. You have to restrict yourself to adding waves which satisfy a certain boundary condition. And as we saw last video, that means working with these cosine functions, whose frequencies are all some whole number multiple of a given base frequency. And by the way, if you were working with some different boundary condition, say that the endpoints have to stay fixed, you'd have a different set of waves at your disposal to piece together. In this case, simply replacing that cosine expression with a sine. It's strange how often progress in math looks more like asking a new...
Deixa eu voltar pouquinho aqui, para mostrar para vocês algo que a gente já fez e que... Cadê? Será que eu viajei aqui agora? Deixa eu rodar de novo aí, né?
When you consider the chaotic frenzy dynamic be perfectly flat, except for a constant function, nor will it... It's strange how often progress in math with these cosine functions, whose frequencies are also and patterns as correlations. If nothing else, this should give you a hint about the general applicability of Fourier series. Now hang on, I hear some of you saying, none of these sums of sine waves that you're showing are actually the step functions. They're all just approximations. And it's true, any finite sum of sine waves will never be perfectly flat, except for a constant function, nor will it be discontinuous. But Fourier thought more broadly, considering infinite sums. In the case of our step function, it turns out to be equal to this infinite sum, where the coefficients are 1, negative 1/3, plus minus 1/7, and so on for all the odd frequencies, and all of it is rescaled by 4 divided by pi. I'll explain where those numbers come from in a moment. Before that, it's worth being clear about what we mean by a phrase like infinite sum, which runs the risk of being a little bit vague. Consider the simplest
só dar uma paradinha aqui.
Or you could say, for example, that this infinite sum of fractions.
Bom, sai cá. Tá, então olha só, deixa eu mostrar aqui uma coisa, questão que vale a pena para as nossas aulas, né? Então a gente trabalha com N, Pi, X, né? Então é cosseno de N, Pi, X sobre P. P tem a ver com a nossa amplitude, né? Que vai de menos P até P, correto? observe que nesse instante, como eu não tenho aqui, ó, ele está dividindo por 3. Esse 3 aqui não tem nada a ver com a... É porque, na verdade, o nosso P para esse instante vale 1. E fica fácil, acho que num gráfico anterior, ou até aqui, ó. Observe que a variação, ora é 1, ora é 0 e ora é menos 1. De 1 até menos 1, né, a gente acaba observando que tem uma distância total aí, que são duas, apesar que a gente pega no x, né? Então, do x igual a x menor que meio, x maior que meio, apesar que aqui não dá para pegar. Mas, de qualquer forma, fica, ó, aqui, por exemplo, vai de 0 até 1. Isso. Então, é essa a ideia. Mas, num outro momento, a gente mostra onde é que aparece essa história do P ou do L. Vocês viram que em um dado momento é chamado de L, né? Dá na mesma. Tá?
Pi divided by 4. As you keep adding the terms one by one, at all times what you have is rational. It never actually equals the irrational pi divided by 4. But the sequence of partial sums approaches pi over 4, which is to say, the numbers you see, while never equaling pi over 4, get arbitrarily close to that value, and they stay arbitrarily close to that value. That's all a mouthful to say, so instead we abbreviate and just say the infinite sum equals pi over 4. With functions, you're doing the same thing, but with many different values in parallel. Consider a specific input, and the value of all of these scaled cosine functions for that input. If that input is less than 0.5, as you add more and more terms, the sum will approach 1. If that input is greater than 0.5...
Aqui, turma, observe que vai... Cadê? Vamos lá, peraí. Preciso aprender a dar umas paradas aqui. Acho que é só apertar o K, né? Preciso aprender isso. Aqui, turma, observe que vai de 1 até menos 1. Aqui, a nossa amplitude total é 2, então você trabalha sempre com a ideia da metade. Então, o tal do P lá vale 1. Tá? É isso.
That means that somewhat awkwardly, for this infinite sum to be strictly true, we do have to prescribe the value of the step function at the point of discontinuity to be 0, sort of halfway along the jump. Analogous to an infinite sum of rational numbers being irrational, the infinite sum of wavy continuous functions can equal, honestly goodness equal, a discontinuous class function. It then allows for qualitative changes, which finite sums alone never could. There are multiple technical nuances that I'm sweeping under the rug here. Does the fact we're forced into a certain value for the step function at the point of discontinuity make any difference to the heat flow problem? For that matter, what does it really mean to solve a PDE with a discontinuous initial condition? Can we be sure that the limit of solutions to the heat equation is also a solution? And can we be sure that all functions actually have a Fourier series like this? If not, when not? These are exactly the kind of questions which real analysis is built to answer, but it falls a bit deeper in the weeds than I'd like to go here, so I'll relegate that all to links in the video's description. The upshot is that when you take the heat equation solutions associated with these cosine waves, and you add them all up, all infinitely many of them, you do get an exact solution describing how the step function will evolve over time. And if you had done this in 1822, you would have become immortal for doing so. The key challenge in all of this, of course, is to find these coefficients. So far, we've been thinking about functions with real number outputs, but for the computations, I'd like to show you something more general than what Fourier originally did, applying to functions whose output can be any complex number in the 2D plane, which is where all these rotating vectors from the opening come back into play. Why the added complexity? Well, aside from being more general, in my view, the computations become cleaner, and it's easier to understand why they actually work. More importantly, it sets a good foundation for the ideas that will come up later on in the series, like the Laplace transform, and the importance of exponential functions. We'll still think of functions whose input is some real number on a finite interval, say from 0 up to 1 for simplicity. But whereas something like a temperature will have outputs on a real number line, this broader view will let the outputs wander anywhere in the two-dimensional complex plane. You might think of such a function as a drop, with a pencil tip tracing out different points in the complex plane as the input ranges from 0 to 1. And instead of sine waves being the fundamental building block, as you saw at the start, we'll focus on breaking these functions down as a sum of little vectors.
Então aqui, turma, ele está mostrando algo muito importante. Esse tipo de desenho aqui, ele é feito no plano de Argand-Gauss, né? Ele está trabalhando com as variáveis complexas, tá?
Constant integer frequency. Functions with real number outputs are essentially really boring drawings, a one-dimensional pencil sketch. You might not be used to thinking of them like this, since usually we visualize such a function with a graph, but right now the path being drawn is only in the output space. If you do one of these decompositions into rotating vectors for a boring one-dimensional drawing, what will happen is that the vectors with frequency 1, negative 1, will have the same length, and they'll be horizontal reflections of each other. When you just look at the sum of these two as they rotate, that sum stays fixed on the real number line, and it oscillates like a sine wave. If you haven't seen it before, this might be a really weird way to think about what a sine wave is, since we're used to looking at its graph rather than the output alone wandering on the real number line. But in the broader context of functions with complex number outputs, this oscillation on the horizontal line is what a sine wave looks like. Similarly, the pair of rotating vectors with frequencies 2 and negative 2 will add another sine wave component, and so on, with the sine waves we were looking for earlier now corresponding to pairs of vectors rotating in opposite directions. So the context that Fourier originally studied, breaking down real value functions into sine waves, is a special case of the more general idea of 2D drawings and rotating vectors. And at this point, maybe you don't trust me that widening our view to complex functions makes things easier to understand. But bear with me. It really is worth the added effort to see the full picture. And I think you'll be pleased with how clean the actual computation is in this broader context. You may also wonder why, if we're going to bump things up into 2 dimensions, we don't just talk about 2D vectors. What negative 1 has to do with it? Well, the heart and soul of Fourier series is the complex exponential, the I times t. As the input t ticks forward with time, this value walks around the unit circle at a rate of 1 unit per second. In the next video, you'll see a quick intuition for why exponentiating imaginary numbers walks around circles like this from the perspective of differential equations. And beyond that, as the series progresses, I hope to give you some sense for why complex exponentials like this are actually very important. In theory, you could describe all of the Fourier series stuff purely in terms of vectors and never breathe a word of I, the square root of negative 1. The funds would become more convoluted. But beyond that, leaving out the function e to the x would somehow no longer authentically reflect why this idea turns out to be so useful for solving differential equations. For right now, if you want, you can think of e to the ip just as a notational shorthand for describing rotating vectors. But just keep in the back of your mind that it is more significant than mere shorthand. You'll notice I'm being a little loose with language, using the words vector and complex numbers somewhat interchangeably, in large part because thinking of complex numbers as little arrows makes the idea of adding a lot of them together easier to visualize. Alright, armed with the function I times t, let's write down a formula for each of these rotating vectors that we're working with. For right now, think of each of them as starting pointing 1 unit to the right at the number 1. The easiest vector to describe is the constant one, which stays at the number 1, never moving. Or, if you prefer, it's quote-unquote rotating, just at a frequency of 0. Then there will be the vector rotating 1 cycle every second, which we write as e to the 2 pi I times t. That 2 pi is there because as t goes from 0 to 1, it needs to cover a distance of 2 pi along the circle. Technically, what's being shown is actually 1 cycle every 10 seconds, so that things aren't too dizzying. I'm slowing everything down by a factor of 10. We also have a vector 1 cycle per second in the other direction, e to the negative 2 pi I times t. Similarly, the one going 2 rotations per second is e to the 2 times 2 pi I times t, where that 2 times 2 pi in the exponent describes how much distance is covered in 1 second. And we go on like this over all integers, both positive and negative, with the general formula of e to the n pi times I t. Notice, this makes it more consistent to write that constant vector as e to the 0 times 2 pi times I t, which feels like an awfully complicated one knobs and dials we get to turn is the initial size and direction of each of these numbers. The way we control that is by multiplying each one by some complex constant, which I'll call C sub n. For example, if we wanted the constant vector not to be at the number 1, but to have a length of 0.5, C0 would be 0.5. If we wanted the vector rotating at 1 cycle per second to start off at an angle of 45 degrees, we'd multiply it by a complex number, which has the effect of rotating it by that much, which you can write as e to the pi fourths times I. And if its initial length needed to be 0.3, then the coefficient C1 would be 0.3 times that amount. Likewise, every one in our infinite family of rotating vectors has some complex constant being multiplied into it, which determines its initial angle and its total magnitude. Our goal is to express any arbitrary function f of t, say this one, that draws an eighth note as t goes from 0 to 1, as a sum of terms like this. So we need some way of picking out these constants one by one, given the data of the function itself. The easiest of these to find is the constant term. This term represents a sort of center of drive. If you were to sample a bunch of evenly spaced values for the input t, as it ranges from 0 to 1, the average of all the outputs of the function for those samples will be the constant term C0. Or, more accurately, as you consider finer and finer samples, the average of the outputs for these samples approaches C0 in the limit. What I'm describing, finer and finer sums of a function for samples of t from the input range, is an integral of f of t to 1. Normally, since I'm framing this all in terms of averages, you would divide the integral by the length of the input range. But that length is 1. So in this case, taking an integral and taking an average are the same thing. There's a very nice way to think about why this integral would pull out C0. Remember, we want to think of this function as a sum of rotating vectors. So consider this integral, this continuous average, as being applied to that whole sum. The average of a sum like this is the same as the sum over the averages of each part. You can read this move as a sort of subtle shift in perspective.
Pessoal, tem uma questão aqui que também é importante vocês observarem. Quando a discussão... vamos parar aqui, parou. Aí. Quando a discussão é no plano complexo, vale a pena esta representação. Percebendo aqui, ó, está chamando aqui, sei lá, vamos chamar aqui de n vezes 2π e t, né? Certo? Que é essa ideia aqui, ó. Menos 1, né? 0, 1. Bom, então, veja. Isso que está aqui, eu poderia colocar desse jeito aqui, ó. É n2πt vezes i, né? Isso que está aqui a gente já sabe que representa, na verdade, o cosseno de 2 de n, né? De n vezes 2πt. Isso aqui é um número. E aí vai depender do n. Mais i seno da mesma coisa, né? Então, observa que a gente trabalha num ambiente real, a gente não utiliza um tal do i, né? Mas, de qualquer forma, o número exponencial de Euler, né? Ele tem essa característica, né? Do ponto de vista de coordenadas, né? De coordenadas trigonométricas, né? Então, por isso que lá no plano de Ardan-Gauss, né? A gente sabe que esse é o eixo do cosseno, esse é o eixo do seno. Exatamente por conta do imaginário, né? Então, os valores do seno estão aqui, ó. Por isso que às vezes você resolve lá seno para o seno, sei lá, deu 2 mais 3i. Então, de fato, aqui é 2, certo? 1, 2, 3. E aqui é o 3. E aqui, então, seria um ponto no plano de Ardan-Gauss, no plano complexo, né? E essa é a ideia principal. Então, quando se trabalha do ponto de vista complexo, evita-se trabalhar com seno e cosseno, que é o que a gente está fazendo lá nas transformadas de Fourier. Trabalha exatamente com um número exponencial, né? Então, por isso que a transformada de Fourier, nesse instante, está sendo muito mais apresentada aqui na exponencial.
And then add up all these averages. But each of these vectors just makes a whole number of rotations around 0. So its average value is the constant term. Since it stays static and doesn't rotate, its average value is just whatever number it happened to start on, which is C0. So doing this average over the whole function is a sort of clever way to kill all of the terms that aren't C0. But let's say that you wanted to compute a different term, like C2, sitting in front of a vector rotating 2 cycles per second. The trick is to first multiply f of t by something that makes that vector hold still, sort of the mathematical equivalent of giving a smartphone to an overactive child. Specifically, if you multiply the whole function by e to the negative 2 times 2 pi I times t, think about what happens to each term. Since multiplying exponentials results in adding what's in the exponent, the frequency term in each of our exponents gets shifted down by 2. So now, as we do our averages of each term, that C-1 vector spins around -3 times with an average of 0. C0 vector, previously constant, now rotates twice as t ranges from 0 to 1, so its average is also 0. And likewise, all vectors other terms make some whole number of rotations, meaning they average out to be 0. So taking the average of this modified function is a clever way to kill all of the terms other than C2. And of course, there's nothing special about the number 2 here. You could replace it with any other n, and you have a general formula for Cn. Out of context, this expression might look complicated. But remember, you can read it as first modifying our function, our 2D drawing, so as to make the nth little vector hold still, and then performing an average which kills all of the moving vectors and leaves you only with the still part. Isn't that crazy? All of the complexity in these decompositions you're seeing of drawings into sums of many rotating vectors is entirely captured in this little expression. So when I'm rendering these animations, that's exactly what I'm having the computer do. It treats the path like a complex function, and for a certain range of values in, it computes this integral to find a coefficient c of n. For those of you curious about where the data for a path itself comes from, I'm going the easy route and just having the program read in an SVG, which is a file format that defines the image in terms of mathematical curves rather than with pixel values. So the mapping f of t from a time parameter to points in space basically comes predefined. In what's shown right now, I'm using 101 rotating vectors, computing the values of n from -50 up to 50. In practice, each of these integrals is computed numerically, basically meaning it chops up the unit integral into many small pieces of size delta t, and then adds up this value, f of t times e to the -n 2 pi I t times delta t for each one of them. There are fancier methods for more efficient numerical integration, but this gives the basic idea. And after you compute these 101 constants, each one determines an initial angle and magnitude for the little vectors, and then you just set them all rotating, adding them tip to tail as they go, and the path drawn out by the final tip is some approximation of the original path you fed in. As the number of vectors used approaches infinity, the approximation of the path gets more and more accurate. To bring this all back down to earth, consider the example we were looking at earlier of a step function, which, remember, was useful for modeling the heat dissipation between two rods at different temperatures after they come into contact. Like any real number valued function, the step function is like a bowling drawing that's confined to one dimension. But this one is an especially dull drawing, since for inputs between 0 and 0.5, the output just stays static at the number 1, and then it discontinuously jumps to -1 for inputs between 0.5 and 1. So in the Fourier series approximation, the vector sum stays really close and stays close to that for the second half of the cycle. And remember, each pair of vectors rotating in opposite directions corresponds to one of the cosine waves that we were looking at earlier. To find the coefficients, you would need to compute this integral. And for the ambitious viewers among you itching to work out some integrals by hand, this is one where you can actually do the calculus to get an exact answer, rather than just having a computer do it numerically for you. I'll leave it as an exercise to work this out, and to relate it back to the idea of cosine waves by pairing off the vectors that rotate in opposite directions. And for the even more ambitious, I'll leave another exercise up on the screen for how to relate this more general computation with what you might see in a textbook describing Fourier series only in terms of real values, with sines and cosines. By the way,
vocês viram? No finalzinho ele apresentou exatamente, né, a forma que a gente trabalha, né? Tá muito bacana. Tá aí, bastante complexo, né? Vamos pegar um último aqui. Uma ideia, cadê ele aqui? Deixa eu ver, esse já foi. Esse aqui, vamos lá. Você vai falar de novo dessa história do discreto.
The discrete Fourier transform is fundamental to many questions in science and technology, and naturally we want to be able to compute the discrete Fourier transform fast. The classical way to do that is the so-called FFT algorithm, the fast Fourier transform algorithm, was first designed in 1965 by Cooley and Tooby, also known as the Cooley algorithm, and has led to a revolution in digital signal processing.
This is Michael Kaperov, an assistant professor of the assistive PFL, and indeed, the Fourier transform is central to our information age. As a result, performing the Fourier transform in a fast and efficient manner has been one of the greatest breakthroughs of computer science. Professor Gilbert Strang of MIT described the fast Fourier transform as the most important numerical algorithm of our lifetime. But why is the Fourier transform so central to our modern world?
This transform is really fundamental to numerous areas of science and technology. You can think of signal processing, data analysis, medical imaging, and perhaps the very well-known example is image and video compression schemes. So think of JPEG.
You do know what JPEG is, don't you? What about MP3? These are digital formats for images and sounds, and there are plenty of other formats for videos as well, like H.264, which is the one I'm using for this video. Such audiovisual files are opened by each and every one of us every day, and every time you're looking at a digital picture, every time you're listening to digital music, and every time you're playing a digital video, some FFT algorithm will be running in the background. As Richard Branyuk, a professor of Rice University, puts it, FFTs are run billions of times a day. But how does the Fourier transform help with audiovisual compression?
In many applications, we acquire signals and continuously. But these signals are usually sampled at discrete intervals, analog to digital converters. So once the signal is digitized, the sample, the question becomes
the classical continuous Fourier transform that was studied by French Joseph Fourier and others in the early 1800s. These days, we rather focus on digital data, and therefore we rather care about the discrete Fourier transform.
Now, if we are trying to compress an image using the JPEG method, what we would like to do is just say, I take an image, I take the Fourier transform of that image, and then it turns out that for most images, because these images are smooth in time domain, the Fourier domain representation is fairly compact. So we just truncate to the top few coefficients in magnitude, zero out the rest, and hence we achieve compression.
Let's explain a bit more. Signals like images and sounds can be regarded as one way of representing some fundamental mathematical objects. The Fourier transform allows us to...
Peraí, mudou a legenda aqui. Peraí.
Look at these fundamental mathematical objects at a different angle. Thereby, objects that look awfully complicated in the signal domain can suddenly appear amazingly simple and easy to describe, the Fourier domain. This will be the case when the signal in the Fourier domain is mostly zeros, in which case we don't even need to record the zero values. We can just store in memory the non-zero values, which means that we need less memory space to record a signal. But why would the Fourier representation of images and sound be so nice and compact in the Fourier domain?
So if we think of a k-sparse signal in Fourier domain, well, this is a signal that is basically a sum of a small number of pure harmonics, plus maybe some amount of noise.
And make it clear why most music are made of only a handful of pure harmonics. After all, that's how music partitions are written. If a musical note imposes a particular pitch, which corresponds to a pure harmonics. In fact, there's even more than that, as depending on instruments, each note is accompanied with a tone which is usually itself a combination of a handful of pure harmonics. However, it might be less images are also made of a handful of pure harmonics. The way JPEG actually works is by first decomposing an overall image into tiny squares. The resolution of the large image is quite high. Each tiny square will likely be smooth and nearly homogeneous, which means that the frequency rotation of such tiny squares will mostly be made of low frequencies. In both cases, it turns out that most of the signals is actually a composition of a handful of frequencies. Now, the other frequencies, they are usually not exactly zero because there's always some noise. But as long as this noise, these amplitudes of the other frequencies are low and negligible compared to the main signal, you can basically just get rid of them, just cancel them out without really affecting the quality of the image or the sound.
The underlying idea of JPEG is that we take a time domain representation, which is the image itself, we take the Fourier transform of that, and then it turns out that if we just keep the top few coefficients and throw away the rest, compression.
This approach has strong resemblance with machine learning algorithms like PCA or SVD, or the representation we discussed with Martin Judd.
This is one reason why the discrete Fourier transform is important, because for natural signals that arise in applications, it sort of concentrates their energy in a small number of coefficients. And hence, just focusing on these coefficients results in savings in storage, savings in time, etc. And the Fourier basis turns out to also be convenient for other reasons. And one of these reasons is the fact that convolution, the operation of convolving two signals, becomes very easy to perform in the Fourier domain.
Wait, what's a convolution and why does it matter?
So here's one reason for computing convolution. Suppose that I have a signal x and some template signal y, and I know that a signal x is basically a shift, or maybe a shift of the signal y in time domain, plus perhaps with some noise added. And what I want is to find out what is the right shift, basically that aligns x and y ultimately. One way to do it is exactly to compute a convolution. So what is a convolution? Convolution is the following operation. We'll take the signal x, and then we consider all the possible shifts of the other signal y, and we do the dot product of x and the shifted version of y. And we basically overlay x with a shifted version of y and check how similar they are.
But why would we ever want to search for the optimal
noisy version of some template signal y?
Yes, because to locate yourself.
Olha lá, turma, que a gente viu lá a operação de convolução, né? Que eu gravei um vídeo para vocês da Transformadas lá. É utilizado, né? Essa operação é utilizada bastante no GPS, né? Quem diria, né? Que tem a ver com essa história de aproximar, né? Mas óbvio que essa aproximação da convolução que eles estão dizendo faz muito mais sentido na transformada de Fourier.
GPS, we need to measure very precisely the communication delay from the satellite to your phone. To do so, the satellite will send you a signal Y, and you know that it will look like some template X. Measuring the arrival time of Y will then boil down to determining the tecton stage of X that best matches the signal Y.
Now the question is, can you find the right shift? Now, if you think of doing this in the direct brute force way, my signal x is of length n, my signal y is of length n, then I need to try all the n shifts. On the other hand, if I can switch to the Fourier domain, it turns out that all that I need to do is take the Fourier transform of x, Fourier transform of y, and multiply them by twice. And then do the Fourier transform back. Then in the resulting signal, if I look at the peak, the maximum, this is the right shape. Multiplication is very easy, convolution is very important. So if we have a way of quickly switching from time domain representation to frequency domain representation, then we can take x and y, compute the Fourier transform, multiply them, compute the Fourier transform back, and we have the convolution of x and y. So this is a fast algorithm for performing convolutions.
The Fourier transform is the key algorithm to determine optimal time translation.
Exactly. So this is a very efficient way of resolving optimal translations of one signal that make it similar to another signal.
More generally, whenever signals have a lot of time or spatial translation symmetries, then convolution and the Fourier transform will be powerful tools to efficiently deal with such symmetries. In fact, inspired by the architecture of a brain, researchers in deep learning have exploited convolution to improve the image processing of their neural networks. This has led to so-called convolutional neural networks, as well as key breakthroughs in object detection and face recognition. So yes, the Fourier transform is a big deal.
But in fact, there are also other reasons. Let me mention one here, and this is something that comes up in medical imaging. For example, when one is performing an MRI scan, one can view this process as follows. So there's this object being scanned, the patient, and essentially the process of performing an MRI scan is this. You can think of the patient as a signal in time domain. Now the MRI machine basically measures Fourier coefficients of the signal x at various locations. Now the question becomes, if I want to scan a signal x of the patient, then this is basically the question of reconstructing x from a small number of Fourier measurements. So this is yet another application where the Fourier transform comes up for completely different reasons, given by the physics of the process.
In fact, this is not so different from what our ears do at any point in time. Our ears are made of tiny hair, each of which can only vibrate at a very specific frequency. Now, because of a physical phenomenon called resonance, our hair will vibrate if and only if it hears the pure harmonics associated with its intrinsic frequency. And when you think about it, this means that our brains are only told about the frequencies of the sound that our ears hear. Yet our brains are able to combine these frequencies to reconstitute the sound that our ears hear. Our brains apply Fourier transform all the time. So in a nutshell, the Fourier transform has a lot of applications. We've barely scratched the surface in this video. And because of it, the fast Fourier transform by Korea and Turkey has conquered the world. But what if I were to tell you that Korea and Turkey's algorithm has recently been outperformed? Well, this is what we shall discuss next time.
Interessantíssimo, né, turma?
That's where the Fourier transform comes in. It comes up with a way to estimate the...
Pessoal, eu vou deixar os links para vocês, né? Tem muita coisa. Eu acho que é importante nesse instante, assim, de novo, que eu comentei na aula passada, né? Procurem dar uma pesquisada, essa é a ideia principal, né? Procurem pesquisar bastante sobre aplicações, talvez agora muito mais voltado para a área de vocês, né? Trabalhando aí com circuitos. Quem sabe já encontrar alguns cursos aí, já cheguei a ver alguns, assim, alguns cursos que trabalham com sinais digitais e que utilizam as transformadas de Fourier em engenharia elétrica. Então, procurem dar uma pesquisada aí, né, porque vale a pena. Se encontrar algum vídeo interessante, mande para nós, porque nesse instante, todas essas aplicações, elas acabam sendo muito importantes aí para esse ensino de transformadas de Fourier. Tá certo? Ficamos por aqui. Amanhã nos vemos, então, no mesmo bate-canal. Valeu? Espero vocês lá. Até mais.